To go. We're going to go on track 2. All right, welcome to the final session of the day at B-Sides and track 2. We have just a brief announcement for those of you that are either speakers or paid for VIP tickets. Just want to remind you the VIP dinner is from 5 to 7 p.m. in what we're calling the VIP room. And if you haven't fully explored the rabbit warren that is this building, the VIP room, when you came in this morning down the hallway where you were checking in to get your badges, when you get to the end of that hallway, instead of going left into track 1, you turn right, and that'll take you into the kitchen area of the area where we're going to have the VIP room and dinner tonight. So for those of you that paid for that and or speakers, please make sure if you plan on joining us that you please do. We hope you're all there. And our next speaker is Farshad, and he's going to talk to us a bit about container security, which I learned a lot last time I heard you speak on container security at the OWASP meeting, I think a couple years ago at Mozilla. Was when I first started thinking more about Docker security and things like that. And Farshad is an innovative technologist, according to this piece of paper in front of me. So please give him all of your attention for the next hour, and over to you, Farshad.
Thanks very much. Can you guys all hear me? Awesome, excellent. Just before I start, I'm curious to see how many of you have ever used containers in any way, shape, or form, if you can put your hands up. Cool, that's good. There's a fair number of people, because when I've done this presentation in different forms, it's sort of a mixed percentage of people, but it looks like there's a fair majority of you that have had a taste of containers. So the talk today, obviously, for the next hour is about container security, and we just want to look at whether containers actually live up to their names and contain the security issues or not. So what I'm going to talk about, we'll just go through a number of things. We'll talk about what is, first of all, let's start with what is computing in the cloud, what does cloud computing mean? And then once we've sort of have a good idea, we're all level set on that, let's talk about what are containers and how do they fit in that model? And then what are the supporting casts? So what are all the tools and frameworks that go with it? Because oftentimes I find that there's a lot of confusion. People throw these names around like Kubernetes and Docker and PCF and this and that, and they call it all containers, right? But they're not all containers. So some of them are the supporting cast. Some of them are the actual container engines. So we're going to clarify that before we move forward. And then we'll look at the differences between containerization and virtualization. And then we'll look at the two more common ones that I'm familiar with, and I know a lot of people in the industry use, which are Docker and Cloud Foundry, or Pivotal Cloud Foundry's Garden. And then we'll look at we'll go over some security concerns to see what people should be concerned about and when deploying containers, and also what are some of the known vulnerabilities in the last couple years that these containers have been in use. And then finally, we'll look at safe container practice, and we'll wrap it up with some points in conclusion. So my personal journey with containers started a couple years ago as the company that I worked for started deploying these things, and they decided that it was a good idea to jump in, and we want to go into the world of DevOps, and I'm sure that's probably a good number of you have become accustomed to using containers through DevOps. And so our organization decided that we're going to go and do this, and we're going to get Pivotal's Cloud Foundry, or PCF, as a platform, and so I was assigned to figure it out, essentially. And my background is, I'm currently the principal security architect for a leading financial institution, but I've got a wide, varied background in terms of when it comes to IT. I've done a fair number of years in software design, architecture, development, as well as a fair number of years spent in system admin, networking, and all that other fun stuff that people would do. So this was really interesting for me, and I sort of have become the security SME when it comes to this at work, just by the virtue that I'm really interested in it. So let's talk about cloud computing. You can see here there's the cloudy Vancouver, right? We're looking at it from the North Shore. This is taken from West Vancouver. It's looking at downtown. There's Lions Gate, and it's very cloudy, right? So cloud can mean different things to people. So cloud can be a great thing, right? So you just put things out there, you don't worry about it. But it could also be kind of like Vancouver, right? It's a bit gloomy and mysterious, and sometimes it could be dark, and you have no idea what's going to happen next. So this picture is a good representation of cloud computing and what I can relate to with respect to my life in Vancouver. And here's a quote from NIST in terms of the definition of cloud computing. So they define cloud computing as a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources, for example, networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort for service provider interaction, right? So this is their definition. How you accomplish this could be a number of different ways, right? So that's kind of what I wanted to talk about, take a minute and talk about, because you can, in order to do that, you need a workload isolation, right? So you have a bunch of workloads, and that needs to, meet the NIST definition. So how you can provide that isolation, there are a number of different ways that you can do that. So you could either accomplish that goal through physical separation, right? So you could literally accomplish that goal, but have physically separate machines where the workload is distributed, and that's your separation boundary. Or you can go into virtualization, or what's commonly referred to as virtualization, but also referred to as hardware virtualization. That's what you guys are all familiar with, like VMware, VirtualBox, that kind of stuff, where vulnerability. So in this case, what we're doing is the hypervisor is your separation boundary, and you can have vulnerabilities in these cases related to CPU or hypervisor issues that could have impact here. And this type of separation is typically used to provide infrastructure as a service, or IaaS, as they call it, right? Obviously, if you do physical separation, it addresses pretty much most of the issues with hypervisor. I mean, you don't have hypervisors, and you also address things like covert channels and defects and hardware protection mechanisms that I'm going to touch on in a bit, right? So if you're really, really concerned, you would go with physical separation, but most of us sort of, move on to the, you want the benefits of containerization or virtualization. And with containerization, your separation boundary is called, also known as operating system level virtualization, and your separation boundary is, well, you share the kernel, but you have like multiple copies of operating system with a single shared kernel. And it's used to deliver containers as a service, or PaaS, platform as a service. So what are the difference between the two of them? Well, with platform as a service, you get a whole bunch of extra stuff. You might get a database and cache and logging services and things like that, whereas containers as a service is just containers as a service delivered as infrastructure pieces without all the bells and whistles that a PaaS would give you. A PaaS has kind of been around for a while. Like Foundry was one of the companies that is well known for offering their PaaS, or the platform as a service. And then the containers as a service is becoming more and more popular, which is somewhere in between infrastructure as a service and platform as a service. And then, of course, you have SaaS, right? Multi-user accounts. That's still a separation boundary, but it's not as strong as the other ones, right? As you go down the stack, the separation boundaries become weaker. I mean, with SaaS, your separation boundary is your user accounts. You're sharing everything else underneath it, even the applications being shared, right? But I mean, if you're doing a PaaS, at least you've got your own application. You're sharing the platform, and then with IaaS, you're basically just getting raw devices. So as you're going down this way, the separation boundary changes. So containerization provides an isolation mechanism required for cloud computing. So we can consider it as a type of cloud computing. So what are containers, right? So we talked about cloud computing and the different models for separation, but what about containers? So containerization, as we said, also known as operating system level virtualization, it's where a kernel allows multiple isolated user space instances. And this concept of namespaces or user spaces is really what this whole thing revolves around. So each instance is a container. So it's also known as a software container, or virtualization engine, or jail, so in case of the FreeBSD jails, or Cgroups. And it seems like a regular mechanism, a regular machine from the inside, right? So if you were sitting in that machine, everything would look like a regular operating system. You wouldn't be able to tell whether you're in container or not, but of course, you're sharing that kernel with all the other container instances that are running on that host. And so it allows you to do encapsulate applications, and it also containers can act as an interface to the surrounding system, and there's kernel provided resource management, so it limits the impact of the container's activities on others, right? So in the old days, we had Chroot, and Chroot has been around since 1979. I mean, in my old days in IT, I used it a fair bit. Back in the day, we were like, hey, you want to deploy an application, put in a Chroot, harden MySQL and harden everything else and throw it in a Chroot, jail, have you, and that's what you did. But chroot didn't provide all the other namespace separations. I mean, all they did was it sort of separated your file system, right? So you got your own root file root handle, and you wouldn't be able to see the real root if you were within that chrooted environment. But if you tried to look at the process IDs, you'd be able to see everyone's process ID and other things. So it wasn't as fancy as what containers do today. So it isolated the file systems for processes and their children, right? So if any children processes respond off of that, they'll also see they would be within that isolation. But it doesn't isolate the other resources that I mentioned, so it doesn't isolate networking or process space or anything like that. And the root account has full view and access into all the different chrooted environments, right? So you didn't have that separation. So containers came along, I think it was around like early 2000s. And what containers introduced was they took advantage of the namespaces to separate the resources. So I'm going to go through that in a bit of a detail, but essentially, we now have the process namespace, the mount space namespace, network namespace, UTS, IPC, and user namespaces, which are arguably the most important ones in this journey of security with containers. Then there's also Cgroups that are used to meter and limit resources and control access to device nodes, for example, like dev/dev, and perform crowd control. So namespaces, I kind of wanted to go through this. I put lots of stuff here, lots of detail, but essentially just what I went over. At the top, I put the user namespaces, right? That's the most important one. And that was the one that wasn't actually implemented until recently. So a lot of the implementations, like when I did this presentation about a year and a half ago, when I first started in this journey of containers and then container security, Docker didn't support user namespaces, and neither did Cloud Foundry. And I think it was about less than a year ago that Docker implemented user namespaces, and Cloud Foundry has also had it for about the last year. But even then, there have been proven vulnerabilities that have been able to break out of the user namespaces. So nothing is for certain. Just because you have user namespaces, that doesn't mean your problem is solved. But what problem does the user namespace solve? Well, what it does is it allows you to map a particular user inside your container to a different user outside that container, right? So if you didn't have that, if you didn't support user namespaces, the root user in the container would be the same root user on the host system, right? So as you can see, the problem with that, if it's the same user, then if you've got a vulnerability in a particular container and that service is running as root, then it'll have the same permission on the host, and because it's a shared kernel, it'll get the same permission into all the containers. So that's a bad thing, right? We don't want the root user that in a vulnerable container to be able to impact all the other containers. So we want this separation, we want this mapping, so that for example, if there's a root user in a particular container, it maps to a non-privileged account on the host. So if it breaks out, it's not able to do a lot of damage. So it is a good thing, it's desirable. A given user ID, for example, root, inside the container will map to a different ID on the host. It's fairly new, and as I mentioned earlier, there have been vulnerabilities at the start when this was introduced. It's fairly large and complex to implement as well. I'm not sure if everyone's got it right, and that's another thing with containers. This technology is relatively new, so more research needs to get done, more things need to get ironed out. I mean, the rule of thumb, as I always say in security, and it should have stood the test of time, right? With anything, with an algorithm, with a system, you always want it to be out there for long enough that people have had a chance to, hack away at it and find the vulnerabilities, right? If something is fairly new and not a lot of vulnerabilities are found, I wouldn't be too comfortable using that. That doesn't give me that warm and fuzzy feeling that it's like, hey, this has been around for a year and not much has been found on it. I'd be more comfortable if this was around for 3 years and lots of vulnerabilities have been found and addressed as such. So system calls and security logic should be namespace aware. That's another problem, and you should check the capability in the correct namespace, right? So you might, incorrect checking may lead to, there's a clone new user and clone FS root exploit type vulnerabilities, and exploits are still possible even with the user namespace enabled, as I mentioned. So what about the other namespaces? Are they important as well? Yeah, they're definitely important. I kind of put them in the order of importance, with the user namespaces being at the top, and of course the network one is quite important because it provides a separated network stack for each container, right? So that you have these different network handles, and it's fairly widely used. There's a NetRaw abuse case that explores typical flaws in this namespace if you're interested in looking that up. There's also the process ID namespace. You want to keep those separate as well. If you don't want to do a PS in one of your containers and see the list of everybody's process IDs, right? You want to be able to, when you do that inside the container, you want it to be limited to the process IDs that belong to that particular container. So the PID namespace allows each container to have a fully isolated process tree. So with an init process that runs as PID1 in that namespace, and then as you spawn off other things, then it'll go from there. So the PID will be different inside the container than on the host, but vulnerabilities have shown that this info can leak as well, right? So again, I keep saying this, none of these things are 100%. Leaks out of these namespaces can happen. So just because we have these, you can't say, well, no, I'm perfectly fine and it's secure and everything else. There's also the mount namespace, which is used to separate the file system for each container. So there's a pivot root system call is used in conjunction with that as well. And then last but not least, we have the two down below. They're not really widely used. There's the IPC namespace, which deals with System 5 IPC and POSIX message queues, if that's your thing. And then there's the UTS namespace, which it's got system identifiers that's used to provide container-specific host names. So that's a bit about the namespaces, why they're important. There's also a couple of other things that are important in this story when it comes to container security, and those are Cgroups capabilities, MAC, and SecComp. So what are Cgroups? Some of you may have heard of them. Some of you may not have heard of them. Cgroups, also known as control groups, what they do is they limit, account for, and they also help isolate usage of things like CPU, all your resources, right? Memory, disk I/O, networking, for a collection of processes. And it can also be used along with IP tables for traffic shaping, right? So Cgroups are important. We want that resource limitation because if we didn't have them, then one of your containers could go wild and use up all the memory or all the CPU. So that's how you put a handle on it. And then there's the capabilities, right? What are these Linux capabilities? Linux capabilities allow you to, the breakdown of the root role into smaller pieces that can be granted to non-privileged processes, right? So if in the past we had a bundle of stuff that the root could do, but we're like, well, it'd be really nice if I could take a little piece of that and then allow this non-privileged process to just do that one thing, right? So Linux capabilities allow you to do that. You can break things down, and then you can assign a slice of that into a non-privileged process so that they can perform that otherwise privileged action. And then, so a set of capabilities are assigned to a process. It carries forward to the child processes as well from there. So whenever you assign something, you're like, hey, if this capability is assigned to this one, if that process spawns a child process, it's granted downwards. Two other things that are important, mandatory access control, or MAC. Basically, these the LSMs, or Linux security modules. Hooks are provided by those things. So AppArmor is one of those. Essentially what this does is these LSMs, or things like AppArmor or SC Linux, they help limit the actions of a program so it can't just run wild and free. And both Docker and Lexi have this enabled, which is a good thing. SC Linux is also an option. I mean, AppArmor is preferred. Everyone is raving about AppArmor. SC Linux is an option, but it's not as well supported and documented, so the preference is given to AppArmor. And then last but not least, SecComp, which is used to filter system calls, right? So we don't want to have, again, just anybody call whatever system calls that they want to call. That could be dangerous. We have two different modes. There's the strict mode, which allows only a very small set of system calls to be performed, and you can't modify it. So if you're in strict mode, that's not customizable. You can't modify anything. But if you're in filter mode, then the filters, you can write custom filters using Berkeley packet filters or BPFs. BPF programs, which allow you to do more finely grained policies enforcement and things like that. Lexi supports simple policies. Docker supports SecComp BPFs. There's a ptrace vulnerability that bypasses this as well, right? There's vulnerabilities for a lot of these things. Okay, so we've talked about a few of these capabilities and security mechanisms, but what do we use containers for? Just real quick here. I mean, like most of you are using them, and hopefully it falls within one of these bullet points here. So, same as hardware virtualization in terms of allocation of finite hardware resources. That's one of the main uses, obviously. It helps you with separation of several applications for improved hardware independence and added resource management, right? So you can package it, an app and its dependencies in a container. It also is fairly commonly used for hosting APIs and microservices. That's what I use them for mostly. That's why we started going down the container path, because we took our big old monolithic applications and we started to slice them up into microservices or APIs, and that kind of goes hand in hand. We're like, hey, I've sliced these things up. I need to put them somewhere. Let's put them in these containers, and then they're stateless, and you can deploy them rapidly, and there's all kinds of other wonderful things that come along with that with that application. So that's a fairly important use for containers. So typically we would call them application containers if that's what you're doing with them. There's also, like, you could categorize them into application containers and operating system containers depending on the use case. They can be used to automate deployment of applications, distribution method for software to guarantee reproducibility. DevOps comes in, right? So DevOps tools for testing and deploying code. Containers can be used as building blocks for paths, right? If you're building a platform, that is one of the key containers of a platform as a service. It can be argued that you could probably do platform as a service with VMs, but typically paths is done with containers, and the common and virtual hosting. And then the last but not least, what about security? Is security a driver for using containers? That's a funny one, right? Because as the technology is maturing, people are just like, yeah, well, that isolation should give you an added security. But it's kind of like where VLANs were, like back in the day when VLANs first came out, for those of you who remember, VLANs were not designed to give you security, right? Like, they invented VLANs to kind of quiet down the chatter and create separation and whatnot, but it wasn't a security-based intention, right? Security was like a secondary to that, and then of course people were doing VLAN hopping and all kinds of other stuff. But as technology matured, both through better practice and mature technology, now we're comfortable with using VLANs, and we're like, nobody will argue that if you want to, you want to separate security in your network, you can go with VLANs, and that's a fine option because we're fairly advanced in that journey. We can now we have the tools and the processes to use them in a secure manner. We're not quite there yet with containers, right? So if someone tells you that containers are we're going to use them for security, it's not, our old CISO was completely against them. He said, containers, I don't even consider them a security boundary. Like, VM is my security boundary because containers are really new, right? But that was 2 years ago. Since then, a lot has changed. Give it another 2 years, they will be a driver for security, but I personally wouldn't say that today myself. So here's some modern implementations. You can see Cloud Foundry, obviously Docker, Lexi, OpenVZ for Linux containers. There's modern implementations make containers easy to use, right? So we kind of started with Cgroups, which was not very easy to use. Even Docker didn't have a lot of orchestration and a lot of that other stuff when it first came out. But as these things mature, they're getting easier to use. They come with ecosystems and tools that allow developers to learn them more quickly and orchestrate things and schedule. And like I said, all the toys that we're going to look at in a minute, and sort of the ecosystem that goes along with it. But the two common ones there, I've listed Docker Engine and Cloud Foundry's Garden. And some of these containers are designed to run multiple processes and services. Some are designed to only run a single service. So the ones that are designed to run a single service, we would call them application containers. Like I mentioned earlier, you deploy a single microservice into them, and that's all that's supposed to do. But you could also use that container to run multiple processes and use it as a virtual operating system. So that would be an operating system container. All right, so the supporting cast. So we talked about the main actors, right? That's our Docker engine and Garden and things like that. But there's all this other stuff that supports them, because without the supporting cast, the actor and the actress would be sitting there kind of useless. So what are the supporting cast here? Well, one of the more important ones are the container schedulers, right? So the schedulers allow, they allocate containers to allow for scale out, load balancing, adding storage or network resources, maintaining high availability and recoverability, right? These are all really important stuff. So if you were just to use Docker Engine by itself, you wouldn't be able to do all this stuff. So you need something like Swarm, right? So Swarm is going to take a bunch of your Docker engines. So Docker Engine, we're going to look at the architecture in a minute, but it's going to take a bunch of those and create a whole group of them or a whole swarm of them and manage them together like that. Kubernetes does the same thing, orchestration. There's Cloud Foundry's Diego, right? So if you're using Garden, you would be using Diego for orchestration, but these are all sort of at the same level, right? They all orchestrate the container engines, whether your container engine is Docker Engine or Garden or something else. And then you've got obviously to package things and stage them. So OpenShift's source to image or S2I is one of the more popular ones. You also have the build packs that Cloud Foundry supports. Cloud Foundry is now supporting a few other mechanisms for packaging and staging as well. And then you also have infrastructure as a service orchestration, right? Because sometimes it may not be enough to have your container orchestration. You may be working on a platform where you might need that virtualization. Like if I'm working on my Mac, I might need to virtualize and use a VM and then use that container that's compatible with my platform, and vice versa. So typically for rolling out the virtual machines that you can have the containers in, you would do that orchestration using Red Hat Ansible or something like Cloud Foundry's Bosch, right? So if you're a Cloud Foundry shop like what we are, you've got Bosch is managing the virtual machines, right? So you deploy a virtual machine, you orchestrate the VMs, and then once you've orchestrated the VMs, you have to put a bunch of containers in the VMs, right? And that's where Diego comes in. So you got two different levels of orchestration, right? Bosch is orchestrating your infrastructure as a service. You've got VMs, and then Diego is orchestrating the containers and doing all that type of stuff. And similarly with Ansible and Swarm, right? You can think of it that way. So there's different levels of orchestration that come into play. And then, of course, and these other supporting CAS platform as a service, so OpenShift or Cloud Foundry itself, right? The entire thing would be a platform as a service. And these tools evolved at the same time independently. So that's a bit of it presents some challenges because they all were kind of happening at the same time and people weren't talking to each other. So there are some compatibility problems. And, as the ecosystem matures, some of these guys will drop off the map. Some of them will stick around, so we'll see what happens. But it is a pretty interesting time for this technology, and there's a lot going on at the moment. So the next thing I wanted to talk about is containerization versus virtualization, because you're all probably wondering, well, what's the big difference, right? Like, yeah, I've heard containers are light and VMs are heavy, but what's the real difference, right? What is going on there? So containerization. Containers share the same kernel, right? So that's why they're good and that's why they're bad, right? Because they share the same kernel, it's really fast to boot them up, right? You don't have to load the whole kernel. You don't have to wait 5 minutes for whatever kernel it is to load up and all that kind of stuff. Kernel's already ready to go. All you're doing is basically loading the container, but that's not much to load, right? You might have some custom libraries or things that go with it, but pretty much the bulk of it is ready to go. And that's why containers are light and fast, because you're sharing it. You don't have to load up that kernel. It's already ready to go for you. So it's a single OS kernel, provides file system access, application process controls, and networking. And you can't use containers with different operating systems, right? Because obviously if it's a shared kernel, if you're running a whatever Linux kernel, well, you can't have a container that's got like a Windows kernel, right? It's a shared kernel. So that's sort of I guess it's an upside and downside because it makes things faster, but it doesn't give you that capability to deploy multiple operating systems with different kernels, right? If all the operating systems that are going to run on that, or all the containers will have to have the same, they have to share the same kernel, have to be of the same flavor. So they're faster, lightweight, and more portable, and they scale pretty efficiently. There's no hardware emulation at all, right? Whereas with virtualization, right, you're doing hardware emulation. The hypervisor is providing an emulation layer in that sense. And then containers use Cgroups and namespaces, so we really are creating that separation through those mechanisms. And they don't provide the same level of isolation as virtualization. Now, on the other hand, virtualization is more mature with an extensive ecosystem, right? Like VMware has been around, probably for 16 or 17 years now. And they allow for mixed kernels, right? Because they're not sharing. So each of the guest operating systems that is running on the hypervisor, it's going to have its own kernel. It can be whatever it wants to be, right? As long as the hypervisor supports it down beneath, there's no problem there. And the host emulates the hardware provided to the VM, so it looks like it is running on separate hardware, right? So that's where the hardware emulation comes in. And the hypervisor is your security boundary in case of the VM, right? And that would, thereby it's more secure than containerization by that nature. The hypervisors have been known to have vulnerabilities that have been exploited, and people have broken out in the hypervisor. So don't get me wrong, it's not foolproof, but the technology's been around for a long time, and a lot of those issues have been ironed out. And again, through mature technology and processes, we can kind of trust hypervisors. Whereas, you've got this kernel. The kernel's got a lot of potential issues. It's a fairly big, large attack surface, and if anything happens, it'll impact every container that's using that. So here in this picture, you can see that here's my type 2 hypervisor, right? So I've got my bare metal server. There's a host OS, and then there's the type 2 hypervisor, and then I've got my different guest operating systems, and each of them full separate kernel. They've got their own binaries and libraries. There's nothing really being shared. Whereas with containerization, of course, you got your server and host OS, but then there's basically that host OS kernel shared amongst all the containers. They may be even shared binaries or libraries, right? So as you can see, these 4 containers, they're sharing all the same binaries and libraries. So if there's a problem with one of these binaries or libraries, it'll impact all of these containers here. And similarly, these 2 are sharing as well. And again, if there's a problem in the kernel, all of these are impacted. But if there's a problem in this kernel, the other 2 are not impacted. So that's just a visual representation. So let's look at behind the scenes, right? So let's look at a little bit of an architectural deep dive into, what does Docker look like behind the scenes versus what Garden looks like. So Docker accesses the Linux kernel virtualization in many ways. So before version 0.9, Lexi was the default execution environment for Docker. So Docker went through Lexi, got to the Linux kernel, but as after version 0.9, run C, which is used to be called libcontainer, which was written in Go, it's open source. It allows direct use of Linux virtualization facilities, so that's what they're using now for Docker. The other ones are still supported. In addition, the abstracted virtualization interfaces are still supported using libvirt and systemd and spawn, but like the primary way for Docker to access the Linux kernel is now through the run C, or also known as libcontainer. And with Docker also, the actions are done to Docker base images. So you have a base image, and then the union file system layers are created and documented to allow for recreation. So it's a nice model. And the Docker daemon, though, it runs as root, right? So just keep that in mind. Here's the Docker engine architecture, right? Like, we're not talking about Swarm, just the basic Docker engine. You've got your Docker daemon, you've got the actual containers, and you've got the client. The client is a command line interface for those of you who've used it, but really under the hood, it's just using RESTful APIs. So essentially, the daemon is exposing a bunch of APIs, and then they've created that command line interface to call those API functions. So if you wanted to, you could also create your own CLI because it's all based on the APIs that are exposed. But at the heart of it, what the Docker daemon does is that when you try to, when you go Docker run or you name a package, if the image is already here, it will simply take it and it'll spin off a container instance from that image, and it might add a few stuff to it. If it's not there, it'll go to the registry and it'll fetch that image, and then it'll spin up a container, right? So the kinds of things you can do through the client, you can do a build, you can do a pull, you can do a run. And so, if we go Docker run something, it's not there, it's going to go get the image. You'll see, oh yeah, downloading image because I couldn't find it, and then it runs that container for you. And then you can take that. So what you saw there, that's like one Docker engine. Now you can put a whole bunch of these. So if each of these were one of those Docker engines, you can put them together, and then you can have this swarm scenario where you've got the managers and the workers, and then now you can have a whole cluster of these things and deploy things depending on where you maybe want some workload to go, right? So one of the use cases that I'm looking at basically is if you have different security requirements and maybe you don't trust the container separation boundary and you think VM is more appropriate, so you could have these different clusters, and then you can tag your applications that you're deploying, and then based on the tag, it can get deployed in a different cluster. So if you have a bunch of applications that are risky, and then something that's really sensitive, you may want to deploy that in its own node, right? So each of these things, each of the container Docker engines would be a node. So then these are swarm nodes, and then you've got a cluster of them together. So you may want to create a cluster for your very highly sensitive applications. You may want to create a cluster for less sensitive applications and deploy them as such through the use of labels and automation through your build pipeline. So what about Garden? Garden is kind of similar as well, fairly architecturally similar. You got the Garden client, they had the Docker client, there's an API, there's a daemon. They kind of follow a similar model. The main difference here is that the backend is interchangeable. So instead of having it all sort of in one, they've separated it out so that you can have the Garden server and then various backends that actually do the container management. So that's your Warden shell daemon and then the actual containers that get deployed. So this is kind of like what you saw in the previous diagram where the Docker container itself was and its relationship to the Docker daemon. So Garden is actually Warden that was rewritten in Go. So previously Cloud Foundry, their offering was called Warden, and then they came and rewrote it in Go, and then also changed a bit of that architecture. They created that separation, that pluggability, and then they renamed it to Garden. And so essentially it has pluggable backends for different platforms and runtimes, specifying a set of interfaces that must be implemented. So today, actually, they even support Windows containers, which is kind of interesting. So for example, container creation, so the set of interfaces are things like container creation and deletion, applying resource limitations, doing a snapshot to allow for redeployment without downtime, et cetera, et cetera. So there's the Garden run C backend. So that's the Linux-specific implementation of the Garden interface. It uses the OCI, which is the Open Container Interface Standard. Previously, it was Garden Linux, right? So that's in the diagram in the picture here. This was Garden Linux, and now it's Run C. But again, this is just it's interchangeable, and you can create different ones for different platforms. App Armour is used for all unprivileged containers, and seccomp whitelisting restricts access to a set of system calls, right? So we saw what App Armour was earlier, and you can see it here in play. And then there's the Warden shell daemon, which is the root process for managing containers and launching the apps. And essentially, it streams standard output and error back to the client, right? So that's sort of the Garden architecture. And then here, I don't know if you can see it at all because it's probably really small, but I wanted to put this diagram because it kind of puts it all together. Because when you think of Cloud Foundry, I know for me, it was really confusing. I'm like, oh my God, Diego, Garden, Bosch, this. How do they all fit together? This is actually a pretty good diagram. So, you can find it on the internet and you can zoom in, but at a high level, all of this, he says Cloud Foundry. This entire thing is Cloud Foundry, right? And then here, in this box, this is Diego. And then within Diego, you've Garden. So this part of it, so they call it the Diego cells, which is the same concept as the Docker, the swarm nodes in Docker, right? Each of the swarm nodes contains the Docker engine. Each of the Diego cells here contains the Garden engine, essentially. So you can see within this Diego cell, you've got there's the executor, and then there's the actual Garden Linux container. And then so within the Diego cell, you got the cells, you got the brains. So that's kind of like the workers and the managers in Swarm, for those of you who may be familiar with that. And then, of course, you've got this is a PaaS, right? Platform as a service. So you've got things like your database, your access control, you've got your logregator, you've got all kinds of other facilities, your routing, and all this other stuff that come together to create what is the platform as a service, right? And down here, you can see that it supports their traditional build packs. This was like the original how Garden or Warden used to work, but they now support Docker images as well, and they also support the Windows containers. So the Cloud Foundry is really expanding their horizons. So yeah. Here's a side-by-side comparison. So as you can see, in terms of features, there's Garden, Docker. In terms of resource isolation and control, Garden has CPU shares, memory swap, network bandwidth, disk size quota. Docker does CPU shares, CPU sets, memory swap, block device bandwidth. In terms of dynamic resource management, it's supported, but it's not used by Garden, and Docker doesn't really support it. And in terms of image management, Garden supports only whole images that can be reused to create new ones, but Docker has that nice layering, which allows for reusing the separate layers, right? Because you got the base image, and then you can keep layering on top of it, which is actually pretty nice. And then can you do container linking? Garden doesn't support it. Docker does. How about exposing ports? They're both the same. Multiple ports per container can be exposed as such. What about security concerns? I mean, I think that's why you're all here, because this is a security conference, right? So far, we've been kind of talking a little bit about security, more of the architecture of these technologies. But in terms of security concerns, so we talked about the namespaces, right? So the user namespace support is really important. It's supported in Garden and Docker, but as I mentioned, it has been shown to be, people can break out of it, and it's not enabled by default in Docker. So if you're deploying Docker, and if you're really concerned, you should enable this, right? Because that's one of the most important namespaces. And without it, processes running as root inside a container can have root access everywhere, right? So it's rather important, but it has to be configured properly, right? Remember I was mentioning earlier, because if you don't configure it properly, you may not check the right namespace, and then you may cause security issues or break programs. And also, namespaces don't cover everything Linux, right? So first of all, they're not 100%, right? It's nice to have them. They help with the security. You can break out of them, but then there's also things that are not covered in Linux that are not covered fundamentally by a namespace. So just because, you're like, yeah, I've got these 6 namespaces and I'm separating these things, well, what about all this other stuff that fundamentally you're not separating, right? That's why, again, we go back to VMs, because you don't have that issue with VM. You're not sharing kernels. You don't need to worry about separating spaces, right? Or that kind of isolation. And then also there's a problem with imperfect design and coding, right? So, I mean, who knows how some of these libraries or utilities or even the kernel, all these things that are shared, imperfect design and coding, right, increases the attack surface. Namespaces leaks are present in many containers, and many containers have had little security analysis, right? Again, technology is somewhat new. Docker came out in 2013. PCF stuff has been around for at least 10 years. I think 2005, if I'm not mistaken. So it's new-ish, but it hasn't been around in terms of really commercially out there. I think, of those of you who put your hands up, if I asked how many of you have used it for more than 2 years, can I see how many of you have used it for more than 2 years? 1, right? So most of you who put your hands up have only gotten into containers recently, including myself, right? I've only been using them since 2015 in that sense. Not counting Trude as containers, because Trude is sort of the great-great-grandfather of containers, but it doesn't provide what we would call containers. But yeah, if you count that, I've used containers for a long time, but not counting Trude, I think most of us haven't. And also, Docker's image verification is not 100%, right? So they do image verification, but sometimes it's not done properly. You can go read articles about it, so it's they kind of make you feel all good about it, but then you read up and you're like, actually, when they're downloading images, the verification sometimes it's not done as it should be. Again, shared kernel. Any vulnerability in kernel can impact all the containers, and operating system kernels provide much more functionality than hypervisors, right? Therefore, it's a larger attack surface. Hypervisors provide a very specific set of functionality, so the attack surface is smaller. Kernel is supposed to be a general purpose. It's for the operating system. There's a lot of different stuff that it does. Therefore, it's got a greater attack surface. And kernels will always have vulnerabilities in containers, and containers directly expose it to programs, right? And containers were not really designed to container security issues. As I used VLANs as an example, or even back in the day, I might be dating myself, but when hubs went to switched hubs, right? We're like, oh, hey, we have network separation, but that wasn't really network separation. It was a byproduct that you couldn't see the other packets, because now in a switched hub, 2 people are talking to each other. But as we all know, you could do ARP poisoning or a number of other things to really break out of it, right? So again, we're in the same sort of situation, at the same point in the journey with containers. A couple other things I wanted to mention are covert channels and defects and hardware protection mechanisms. These are relevant not just for containers, but also for virtualization in general. But there have been a number of cases where people have been two containers that are not supposed to be able to talk to each other have been able to talk to each other through the use of covert channels, right? So that provides the capability to transfer information between processes that are not allowed to communicate through policy, or you've not linked them together. So it can be done through storage channels or timing channels. So you can communicate by modifying a storage location, and then the other containers watching that storage location, and then they can pick up what is the message can be transmitted. Of course, it's fairly slow to do that, or through timing channels. So you can perform operations affecting response time observed by the receiver. So you're performing some operation, and the receiver is watching something happening, and that response time can be used to calculate the message or decipher the message that you're sending across. It's difficult to completely prevent the issues with covert channels on the same processor, because as long as the processors are running on the same processor, they could technically observe these types of behaviors, right? One example could be like how many times a file was opened, right? And that could be, from a perspective of trying to figure out if this is abnormal behavior or not. Well, opening a file is not abnormal behavior, but if you were intending it to be as such and observe the pattern of file opening, then it can be used to transmit messages across when you're not supposed to be doing that. So it's difficult to catch them. So techniques for locating potential covert channels are analyzing the resource of a system or doing source code level analysis. But again, looking at the file opening example, right? To try to analyze, well, okay, let's look at all the files that are being opened and see if there's something funny going on. Well, how can you tell whether these files that are being opened are being done so maliciously to transmit some idea across to another container? So it's difficult. The possibility can be reduced by careful design and analysis, right? So that's the best we can hope for. And then there's the defect and hardware protection mechanisms. So computer hardware is pretty complex, and some defects can have security implications, right? So there was the rowhammer bug that was used to gain kernel privilege, right? So you can enable changes to values in other programs or kernels. So the rowhammer bug, for those of you who remember, it was a couple of years ago. It happened by the one process changes the voltage repeatedly to a row of memory cells, and then the electromagnetic field induced the other one was able to observe the changes and then pass the message across, right? So you can go read more about it, but that type of issue with the DRAMs, and I think Google were the ones that were able. There was a team from Google. I can't remember the name of that team. Project Zero, I think it was called. I can't remember the name right now, but they demonstrated that exploit on a variety of systems. So yeah, that can be done. Let's look at some known vulnerabilities, because there have been quite a few known vulnerabilities with these technologies. So I looked them up on CVEs, and there were 13 vulnerabilities identified to date against Docker. And I don't know if it's visible or not from there, but you can see there are a number of them. So the more recent one published on 2017-03-02, so like pretty much in a couple of, what is it today, the 13th, so not that, less than 2 weeks ago. It was a race condition in Docker engine before 1.12.6, which might allow local root users in a container to gain privileges by using ptrace to access file descriptors of a process launched or moved into a container from another namespace. So I mentioned that earlier when we were going through the namespaces. I mentioned the ptrace vulnerability. This is also known as the on-entry vulnerability. And then there have been quite a few others resulting in a range of threats. Everything from code execution to information disclosure. So you can hear there's gaining information, gaining privileges, bypassing something, overflowing code execution, denial of service, and that gives you the 13 that they've come up with, and like as recently as this month. So don't let someone tell you that these are perfect and there's no problems with them, because there are still problems. With PCF, 17 vulnerabilities identified to date. Most recent ones that I just pulled a few of the more recent ones for the discussion here. Potential to subject the Universal Account and Authentication, or UAA, OAuth clients to a denial of service attack. There was another one, credentials returned from service brokers are logged in the cloud controller system component logs, and then are written to disk and often sent to log aggregator via syslog. There was another one where it allowed attackers to gain privileges by accessing the UAA logs and then subsequently running a specially crafted application that interacts with a configured SAML provider, and then other vulnerabilities as well. So you can go to the CVE repositories and have a look, but there's ones related to bypass, elevation of privilege, et cetera, et cetera. So, okay, great, all these vulnerabilities, all these things. How do you securely use containers? How do you contain the potential harm, right? As these are supposed to be containers. So some of the things you can do here, you can group containers on a given VM based on the classic segregation principles, right? How did you separate your network, right? Back in the day when you were building a network, you didn't just build one flat network and put all your users in it, right? You could have done that. Some companies do that. Actually, lots of companies do that. But you're not supposed to. What you're supposed to do in proper network design, you're supposed to go, hey, these 5 users kind of have the same requirements. They're my accounting department. They're dealing with financial data. These 10 users are my careless salespeople that just click on any button and download anything. And then these 10 machines are my servers. And so based on what function they were providing and the sensitivity of the data, you would take those users and segregate your network, right? The same classical principles of segregation can still be applied to containers, right? So what you could assume is you could assume that the container boundary is not secure. So you could say, okay, VM is my separation boundary. Given that, so what do I do to put these things together? So you take all your applications, services, microservices, whatever they may be, and apply the same principle. Group them. Okay, these 6 are handling really highly classified data, and if they broke, it's very high impact. And these 5 over here, they are not handling sensitive data, and the programmers that created them were careless, so I'm going to put them together. So do that, and then obviously systems like Docker have mechanisms that allow you to apply tags when things are being deployed through your dev pipeline and put them in different clusters if you're using Docker Swarm, for example. So there are mechanisms, and with PCF, they offer the elastic clusters capability, right? So that you can create a cluster, so you could take 6 VMs and put them in a cluster, and that's cluster 1, and you can take another 10 VMs and make cluster 2. So when you're deploying a container, you can say, hey, this container is highly sensitive, it's going to go to cluster 1. This one is not sensitive, it's going to go to cluster 2, right? So you can automate that through your dev pipeline. But don't forget, the principles you would apply would be, again, nothing new. You know, we've been doing this kind of security separation for a long time, creating security zones for various things, you know, like network segmentation comes to mind. You can apply the same principles here using a risk-based approach, considering the impact and likelihood of that particular application. And services, obviously, should be run as unprivileged. That's nothing new, right? Any of you who have been doing, you know, system administration, sysadmin type work, you would know this, that you should try to not run things as root. And privilege should be dropped as soon as it's not needed. So if you do have something that needs to escalate and get privilege, then you should try to drop that as soon as and that job is done. And you should treat root inside a container as if it was root outside the container. And you should only run containers from trusted parties, right? So don't just download something you don't trust, because who knows what it's going to contain. Again, that's nothing new in this case. And you should follow a layered defense approach. So you should use Armour or SC Linux in addition to all the other stuff. So that's a mechanism for supporting access control, those security policies, right? So just because you separated the containers and you're like, okay, I've created separate security zones and I've separated them, that may not be enough, right? You should still follow the layered defense approach, you know, configure Armour, configure policies, seccomp, all the other stuff, right? Security is all about doing as many things as you can in all the different layers, and hopefully if one fails, you've got something else that will help prevent the attack from taking place or being realized. What else can you do? You can standardize and verify hardened host OS. You can scan containers for vulnerabilities. Hey, as you're rolling these out through your dev pipeline, you should scan these. And that's one of the nice things about containers, and one of the DevOps models that people are going with these days is that you deploy these often, right? So in the old days, we had a physical box, we installed Linux on it, and we installed this heavy, you know, Apache and MySQL and all this stuff, and it was like, heaven forbid, we had to go patch this physical box. It was a nightmare, right? But now you're just putting these containers every day, every week. You're just, you know, you're deploying a new container. You know, something dies, even on the spot, your scheduler might redeploy a container. So that's an opportunity, and these things are all virtual, so that's an opportunity for you to rescan, to patch, and to put all these things back in there, and which we didn't have that opportunity with the old physical system model. So you can, you know, you scan for open source modules, licensing, malware, correct configuration, all those kinds of things you can configure through your build pipeline. And you should measure the containers and sign them, right? So you should analyze and sandbox containers, build a profile. You should confirm signatures at boot, confirm host OS integrity. You should monitor and detect anomalous behavior, you know, all that standard stuff, alert, log, or try to prevent. And you should analyze the user's logs to see if you can identify any weaknesses, right? So if you can adopt patterns, if you can share learning across different instances and things like that. So in conclusion, containers are good, right? We want to use them. I'm not here to tell you that, hey, there's all these security problems, so run away. There's a lot of uses, and we looked at a whole slide full of why you'd want to use containers, and I think a lot of you realize that. They help ease software management, so lots of value in using them, but just got to do that security. So work is being done to address the security issues. Implementation of user namespaces is a big one in the recent year or so. That wasn't there. That's been a big leap forward for security. But they should be used with caution, right? So even with the namespaces that are implemented, you can still break out of them. Their processes in the container should not be given privileged access. They're good for deploying apps that are trusted, so from the same vendor. Other mechanisms such as SE Linux, seccomp, Armour, and separate user accounts should be used in conjunction. And I think I'll wrap it up with that, and I'll open up the floor for Q&A if there's anyone that's got any questions. Hopefully I'll know the answers. I don't know all the answers, but please shoot. There's a question back there. I have not used it, actually. No. What's Docker, unfortunately, I won't be able to give you a good answer on that. But Docker offers a bunch of good tools on their website. They're listed. I'm primarily using PCF, and we're not using any of those in our environment. So look up Docker's website. They've got a list of tools that are used for that purpose. But for Cloud Foundry, I actually should probably look it up because I need to actually start rolling that into my own pipeline. But I don't know the answer to that. No. Yes. Hi, how's it going?
I was wondering if you've taken a look at things like AWS Lambda, the serverless.
Just starting, actually. Yeah, if you want to, we're just like jumping into AWS, and we're kind of trying to merge what we've learned in PCF and bring it to AWS and see if there's any value. But can you elaborate on that? Because I know you're an Amazon expert, so.
Well, I mean, I think it's the next step beyond Docker.
Okay.
For sure. And
What advantages does it provide?
well, it's a lot easier to set up.
Okay.
Basically, you just write the code and it runs the function for you.
With Lambda?
Yeah.
Yeah.
Yeah. So it just has Amazon's built.
So if you're trying to do like a microservice, that's probably the way to go because you don't have to set up all the heavy, like all the other stuff that's involved in setting an OS and putting this microservice in it. You can just put it in Lambda and it'll, is that how it works?
Yeah, more or less. And then if you have something like the Amazon API gateway.
Yeah. Yeah, we're just exploring that. I think we're going to be going in that direction with Amazon. Cool. Thanks. Yes, sir.
Hey, thanks for a great talk. I think defense in depth is an overarching theme of the talk. Are you aware of any tools or methods of managing, like you take an example of a whitelist, you want to apply it to your application, to the network, to the network context, etc. Do you know of any tools to help manage that along each step of the infrastructure, like a tool like Redis or something that's available at all stages?
So what do you mean, like in terms of, I just want to make sure that I understand the question. So in terms of what you're deploying into your container or in terms of how it's configured? Because I mean, there's quite a few different places where you can do that, right? I mean, you can enforce the policies with Armour, you can do the seccomp policies, depending on what you're trying to target, right? Like is it an application access control, which you can accomplish with Armour? Is it access to resources? Is it
More of a tool to help manage the whole
pipeline?
line of defense.
Yeah. Like to check to see if you've got certain things in place or not. Like we do that sort of thing, like we're using Jenkins, right, in our environment. So through Jenkins, we enforce, we basically configure a baseline, like what good looks like. And then it's like, if you're deploying it, then it should have this configured. It should be like this and this and this. So when you run it through that pipeline, it looks for that. And if it falls outside of that, it'll flag it and says, this doesn't fit. So not accepted, right? Is that kind of like what you're?
More of like, we'll take an example. I want to restrict this application to run as this user in this network, and I need to configure my firewalls to whitelist this, block of IPs. I want to configure my application to whitelist these IPs. I want to configure, like that's a good enough example.
To profile the application, what it can or cannot do.
If I'm restarting my containers and that whitelist needs to change, a tool to manage that piece of change throughout the steps of the infrastructure. So if you think of the infrastructure as like an onion,
Yeah.
manage that change in whitelist or blacklist or whatever.
What the changes that have been propagated. So if there's like a new thing you got to add to your whitelist, we do that all of our we do that through our configuration, like through our build pipeline. We manage all that configuration stuff through, as I mentioned, through Jenkins. But that's what we have a configuration repository. We configure what should be, and then if there's a change in policy or like whitelist in your example, we would just put that in the configuration repository, and then that enforces it on the pipeline, and it deploys it as such. That's how. Ansible, you could do that as well. Yeah. Absolutely. No, good question. Thanks. Any other questions? Yes, sir.
Just now you mentioned that you check the configuration of
We're not, so for one thing, I'm not using Docker, I'm using we're a Cloud Foundry shop where I'm using, but it's the same principle. So, I mean, we have, standard config, we baseline a bunch of these configurations, right? So when we're rolling these things out, like we just check and see, does it fit that baseline? Does it fall outside that baseline, like what the developers built, right? So we say, these are the things you should have when you're deploying this container. You should have A, B, C, D, these policies should be enforced, seccomp should be like this, et cetera, et cetera. And if it compares that and the developer is doing something else outside of that, it'll fail. So it won't roll out that container. So you could build that into, that's part of, like, depending on what build pipeline you're using, you could do those customizations within your build pipeline. Yeah, that's the idea. And even with AWS, like right now we're going in the AWS journey, but we're trying to do the same thing because it's all about automation, right? Because we've come up with we had a workshop, 2 days, we sat around and we figured out these are all the things that we should have in terms of security controls, right, for AWS. But we don't want to manually go and enforce those. I mean, it doesn't make sense. So we build an automation through scripts so that someone's deploying it, it'll look for all those things to make sure that they're in place. Whether it's a particular version of TLS, or whether it's something that maybe you should have like mutual authentication between whatever the configuration may be, we usually enforce that through our build pipeline. Yeah, yeah. Cool. Any other questions? Okay, well, if there are no other questions, I thank you very much for coming. Thank you for coming to B-Sides. Hope you've had a great first day. There's going to be more excellent talks tomorrow, and yeah, enjoy. Thank you. You must know a lot of my friends. Do you know Dong?
Yes.
Yeah, he used to work with me at HSBC.
Oh,
yeah,